So in this part of the lecture, what we're going to see is a transformation that is widely used in laser meta-interaction like meta-interaction. And it's a good example of how you can go from one representation to the other. And this is going to be very helpful depending on the system you're dealing with. So this is in fact called the Goeppert-Meyer transformation. So named after Maria Goeppert-Meyer, who was the person who came up with it. And she has made a lot of contributions in multiphoton processes. In fact, she was the first person who predicted that multiphoton processes could occur. She won the Nobel Prize for the shell model. And she did a lot of stuff in maths as well. So we're going to have a look. So to have a look at this transformation, what we are going to need to have is we're going to start from this Hamiltonian. For someone who has never heard of it, this is the minimal coupling Hamiltonian of a particle of charge Q, mass m, in a light field. So here you see you have the momentum operator of this particle. Here you have the vector potential, which is a function of the position operator and of time. And here you have the binding potential. You can see this is a fully time-dependent Hamiltonian. So a lot of things that you see for time-independent conservative systems is not going to apply. Now, we have then this vector potential. We have the momentum operator, the position operator, and the Coulomb potential. And we would like to show that in limit of long wavelength, this means if we can approximate this vector potential that is dependent on R and T by its value at the origin, so that it is only time dependent, doesn't depend on R, this Hamiltonian 1, which we have defined here, is equivalent to this other expression, which is this Hamiltonian 2, where you have P2, this is an operator again, over 2m plus VR, and here you have some coupling with the field that has some kind of dipole form. We're going to discuss this in more detail soon. So this is a velocity gauge Hamiltonian, as is known, and this is a length gauge Hamiltonian. That's how it's known. And we're going to prove, and this E is the electric field, which is minus GA dt. And if you apply this unitary transformation specifically, you can go from one gauge to the other. So this is what we call gauge equivalent Hamiltonians. And the key idea is that the physics doesn't change. It shouldn't change. But sometimes one picture is better than the other. For instance, in one case, you are looking at some potential that may be described as an effective potential. And in the other case, you have like a transverse field. So I'm going to do a whiteboard type derivation of this, and we will see details. So we're going to start from the velocity gauge Hamiltonian. Which is given by H1, 1 over 2m p minus q a r t square plus v r, whereby p and r are operators. So this is describing a particle of charge q and mass m in an external field, and this guy here is the vector potential. So if you're struggling with that, have a look to minimal coupling. Hamiltonians. And you see what I'm talking about. But for our purposes is we want to show that if you can assume, so we want to show that if A RT can be approximated by AT, then this Hamiltonian is going to be equivalent. Then H1 is equivalent to H2 P squared over 2M plus VR minus QR ET. So, and here ET is minus GA GT. So this is a big assumption. This is an assumption that we make when we have, for instance, long wavelengths, that the vector potential does not depend on the coordinate of the system. So we're going to have a look at this, and we are going to apply the unitary transformation that is given, which is x minus 1 over h bar QR scalar product with AT. And we know that H2, so this is something we have derived. We know that H2 T is T H1T T dagger T plus IH bar GT DT T dagger. We know that. So we need to apply all these to H1. So the first step is to compute this guy. So I want to compute this, whereby we have H1. So this is going to be then, we know what H1 is, so we're going to have 1 over 2M T applied to P minus Q A T square T dagger plus V, we do this slowly, T dagger V R T. Now, there's one thing that is interesting. Look at the expression of T. So I'll put TT. Let me write this nicely. So TT is a time-dependent transformation that depends also on R operator, but it depends only on R. So if you have a transformation that is a function of R, so this is T, put T here, let's not be sloppy. This is a function of the operator R. This means that T, no, this is the other way around, sorry. This dagger is here. This means that T VR is equal to 0, correct? So if this happens, if they commute, I can then say that this guy, which I'm going to surround in purple, and I call this true star. So true star is going to be VR T T T dagger T. Now, we said this is unitary, right? So if this is a unitary transformation, we know that T dagger is going to be, so T dagger is going to be the identity operator. So this is something that is very helpful for us. Let's go back to the other one, which was this guy. So this, I'm gonna paint differently. Orange, how about orange? Let's make this orange. Call this double star, and we want to compute this. Okay, so let me compute this. So computing this double star here. What I'm going to have is then T, put like 1 to M, T, P plus Q, A, T, square, T dagger. And this is going to give me, I can make a trick. This is like, if I look at this looks as if I were applying the operator twice, right? Whatever you have a square of an operator, so applying this twice. So I can use this fact, and I can write this as 1 over 2m T P plus Q A T T dagger. Let me see what order I want. I want T dagger T. And then here I have again, I'm omitting the T in the transformation because we know it's time dependent. It's just I don't want to carry it all around, okay? But bear in mind that you do have T's here. And you have then P, Q, A, T. There you go. Now look at how interesting. We have something that if you compute this, you are just going to have the square. You just have to be careful that you do this and the scalar product when you compute the square, but it's like pretty much the square of this. So I have to compute this once, and this is my task. So I can show that T, P plus Q, or minus, sorry, minus Q, A, T, T dagger is putting this E minus I, Q, R, A, T divided by H bar. So I'm just putting the transformation. P plus Q minus, getting this wrong, minus Q A T. And then let me make some space. And here I'm going to have then E I Q R A T over H bar, which is T dagger. Still not nice. Let me see. And the vector is in the wrong place here. Okay, so let's have a look. And we can show that this is going to give you, this is what we call a translation in momentum space. I'm going to give you more details afterwards, but for the moment, we're going to assume that this is correct. So when you apply, so this is what we call translation in momentum space. So when you apply T as it's written to P T dagger, this is going to give you P plus Q A T, whereby this is of this form T. So if this is the case, when we do this computation, we should then get that T, P minus Q, A, T, T dagger is P plus Q, A, T minus Q, A, T. So see what is happening, this will cancel out. Note a few things here. When we did this step that we said, okay, I have this, I'm gonna do a trick to make my life easier. I use the fact here that this is unitary, otherwise I wouldn't be able to do this. So I know that T dagger T, which I inserted here, is the identity operator. Here, put this to make it clearer that you are gonna take the scalar product. And it's much easier if I consider it doing this way than if I have to compute this with the square. It's a really nice trick. And this is something we are going to show subsequently, or maybe you are going to show in an exercise sheet. But notice that these don't commute, because here you have the operator R, here as well, and here you have P. And in fact, when you apply this doesn't just go through, you're going to have this shift. And this shift is going to give you then something that is going to cancel out with this other expression. Therefore, you just get that if you put everything together, we find that this first part, which we said, okay, make this brown. So I'm gonna go, was brown? I don't know, I wanna make it orange, but it looks brown. So yeah, this guy, if I write, I can say that this, how many stars is, yeah, is going to give you P2 over 2m. And the other one, which was the purple one, which is this guy. So make it purple, is going to give me VR, because all this commuted. So I can say that TH1 T dagger is going to be equal to P2 over 2m plus VR, whereby P and R here are operators, okay? Now note the following, that your coupling with the field is gone. You had a coupling with the field via the vector potential, and now this coupling is gone. It has pretty much disappeared because we have this kind of translation. So now what we need to compute is I H bar dt dt T dagger T. This is what is missing. So if I compute, I mean, look at the expression that you have. You're going to have that T is this exponential here, right? So using T, I'm going to get minus I, and what I get down is minus I divided by H bar. You have plus I, sorry. R dA dt E I H bar Q R, sorry, the H bar is below, Q R scalar product AT divided by H bar multiplied by E plus I divided by H bar Q R scalar product AT. So these two cancel out. So this is in fact something I expected because this is T and this is T dagger. Now, because it was an exponential, when you take the derivative of T with regard to time, you get all these things down. So if you rearrange this, you see that you're going to have minus I square. This here is going to go. And this is, I square is minus 1, so you get 1 from here. And you have R dA dt. But we have seen that this dA dt, this is minus the electric field. So you find, and you have Q, sorry, I forgot the Q. There's a Q missing here too. So you find that IH bar dt T dagger T is equal to minus Q R ET. So to summarize, then we're going to have that this is the expression for Hamiltonian 2. I'm bringing everything together. So I find that H2 is P2 over 2M plus VR minus Q R scalar product with ET, which is the length gauge Hamiltonian. Now we need to do a few observations here, and we're going to have a look. So the first thing I would like to call your attention to is that in order to obtain H2, we have used, when we said, let's neglect the spatial dependence of the vector potential, this is what we call the dipole approximation, because this is an assumption that states that if the wavelengths of the field are long enough, you can neglect spatial dependence. And in this case, you can view the Hamiltonian describing the interaction between light and the charged particle as a quantum mechanical counterpart of a charged dipole. And a classical dipole has a dipole moment which is given by this. By the way, these tildes here are vectors. Okay, it's just my dyslexic friendly font does this, I don't know why, where R describes the displacement between positive and negative charges. And if you look at the classical dipole, the interaction energy is going to be given by this, where ET is the external electric field. Note as well that if you want to calculate a relation that looks like that, we had something like this related to our unitary transformation involving P, and where the operators X and B don't commute. Note here, X can be anything. It's not only the operator X position that we know. Okay, you can use the Baker-Campbell-Hausdorff formula. So you expand these and you're going to get this type of relation where you have commutator of B with X, the second order commutations, and so on and so forth. And for the specific case of the momentum translation that I have used here, you can write, if you want, to prove it, you can write this exponential that we had at the beginning like this. So you just invert and you put plus the commutator, and then to calculate the commutator you just have to expand this exponential, which is similar to what we have done in the synchronous lecture for the time evolution operator. And when you do that, then you get this expression from the commutator, which is the one that I had, which cut with the other expression. So that's it for today. Thank you very much for your attention. And our next lecture is going to be about three very important things or representations that are used, which are the Schrödinger picture, Heisenberg picture, and interaction picture. You're gonna see them your whole life. Okay, thank you. Have a nice evening.